Hello everyone. So last day we were discussing about a very important formula on refraction at the spherical, convex and concave spherical surfaces, right? So last day I just mentioned that if we keep all these notations to be same, then we can derive the same formula for all cases, whether it is for the convex spherical refracting surface or concave spherical refracting surface, whether the object is in rarer medium or in denser medium, whether the image is formed in denser medium or in the rarer medium. So by keeping the notation of all these terms same, the object O, image I, center of curvature C, this point as where light ray is incident as M, this is A, this is M, and these angles alpha, angle made by the incident ray with the principal axis, angle made by the refracted ray with the principal axis as beta, and angle made by this normal at point A as gamma. So if we keep these notations same, we can get the formula easily. So during the derivation we come across this term here. This is the final formula we get, and on substituting the values of PO, PI and PC according to sign convention, we can simply get this formula here. So this is the formula what we have discussed last day. Similarly, we can find out the formula for the other cases, right? So we see that all these situation has one formula, and all situations on the other side, these situation will have the other formulas. There is slight change. These values are interchanged and also these values are also interchanged. So this is the only difference. So in all we get only two formulas for all the cases. Once you practice, you will easily learn that these two formulas are the only one which we get in all these cases, right? So these are only the two formulas which we get here. Now we can make use of these two formulas to derive a very important result called as lens maker's formula. It is the formula, the lens maker's formula, which manufacturer of the lens make use in order to fabricate or manufacture a lens of particular focal length from the given value of its refractive index. So let us start to derive the lens maker's formula. So for this, we consider a convex lens just like this, which is convex on both of its sides. So such a surface or a medium which is enclosed by the two convex surfaces, it is called as a convex lens. Sometimes it is also called as biconvex lens or simply a lens, convex lens. So we give it name LM. Its aperture, it is given the name LN, right? C is its optical center. The center of the lens, it is called as the optical center. These P1, P2 are the poles of this lens. Okay, now we have placed object on the principal axis from where the light rays coming and incident on the lens. They meet this first surface of the lens. The first surface, it is called as LP1N. So what happens at this surface? The refraction takes place just as the refraction took earlier in case we have discussed here. So refraction takes place and some image will be formed on the principal axis. But there is another surface which just again changes the medium for the light ray. So if this second surface, if there is no second surface LP2N, only this surface is there and the medium extends to further, then this refracted light ray, which gets refracted at point A on this surface LP1N. If the medium remains same after this surface, which is the glass medium, then this refracted light ray would have traveled and met the principal axis at point I1, and hence the final image would have been formed at point I1. But now, because there is another surface LP2N, so due to this surface, the light ray just bends even more, so that to meet the principal axis at a closer point I. So we see that actually the image is formed at point I due to the presence of this second surface. So in this way we say that whenever, in case of a convex lens, whenever the light rays are coming from the object, its virtual image is to be formed at point I1 and the real image is to be formed at point I. So we can write the two formulas as we have discussed earlier, these two formulas which we have discussed for these cases and then for these cases, right? uh, Directly here we don't remember or we don't do all calculations again, but we just make use of these results. So if the students want to easily derive these formulas on lens maker's formula, then they have to remember these two formulas which come from their previous article, right? So for this surface LP1N, in this case image is formed in the denser medium. How? Suppose that there is no second surface, then this refracted ray would have met at point I1 on the principal axis, and we are going to make use of that representation, right? So we are taking that this refracted ray is meeting at point I1. So for that case we have one equation. You can just remember this equation. It is mu1 upon CO plus mu2 upon CI1, because the image is at I1, and on the other side we have mu2 minus mu1 upon C1. So C1, it is the center of curvature. So how this result is similar and different? Let us focus at this formula as we have discussed here. Here it is PO, PI and PC. All other terms are same. It is P because in case this was only a one spherical surface, and here we have two spherical surfaces. So here in case of lenses, all the distances according to sign conventions are to be measured from its center. This is called as optical center of the lens. So in case of lenses, right, all the distances are to be measured from the optical center of the lens, not from its poles P1 and P2. So therefore it is just P is just replaced by C, the center of curvature of the lens here. So that's why it is CO in place of PO and CI in place of PI and C1 in place of PC, right? Because for that the center of curvature is C1 for this surface. Now what happens? There comes the second surface. Now we will see how the final image is formed. It is formed at a closer point I. So because there is second surface, so it is bending. Light ray is bending again because light ray is moving from a denser medium to the rarer medium, and it is bending towards the away from this normal. This is the normal C2 N2 at this surface. This is the normal here, right? So it bends away from the normal. Whenever light ray goes from denser to rarer medium, it does just bend away from the normal. So by bending away from the normal, it is meeting at a closer point I. Now for this surface, right, this surface, the light ray is coming from the denser medium, right? So therefore we can say that the object will be lying in the denser medium and its final image is formed at point I, which is in rarer medium. So for that situation we have a second result just as this, right? So for this we have here minus CI1 plus mu1 upon Ci, which is equal to minus mu1 minus mu2 upon C2. So this is the only difference here. For the first surface we have one formula, and for the other surface we have to remember the other formula in terms of its general form. Now by making use of these two equations we can proceed for the lens maker's formula. So how do we proceed now? We just add these two equations. Their left hand side is added to the left hand side and right hand sides are added to the right hand side. So on the left hand side, this term mu2 upon Ci1, it just cancels out with this term which is negative, mu2 upon Ci1 negative. So it just cancels out. So on the left hand side we are left with only these two terms, mu1 upon Co from the first equation plus mu1 upon Ci from the second equation. which is equal to, on the right hand side, we just take this term mu2 minus mu1 common here and here, and inside we are left with only this equation, right? 1 upon c c1 plus 1 upon c c2. So this is the final general equation which we get here. You can pause anytime between this class and just observe what I am just mentioning here. Now, by making use of sign conventions and substituting the values of CO, CI, CC1, CC2 according to those sign conventions, we get this equation. Here mu1, it is taken to the right hand side, so on this side mu1 is taken common, on the other side it will just divide. On the left hand side we are left with only 1 upon CO. So this is CO, which will be negative, so it is minus U. Ci, this is Ci, it will be positive along the direction of incident ray, therefore this will be positive V, which is equal to mu2 minus mu1 upon mu1, and inside the bracket we have 1 upon R1 minus 1 upon R2 according to sign conventions, right? Okay, so before we proceed further, I want to once again mention what just we have did here. So here is a lens which is nothing but a glass medium which is enclosed by two convex surfaces, so it forms a lens, convex lens. So here object is placed on the principal axis, so light ray is coming from this object, it meets this lens at its first surface LP1N, right, at point A. If there is no second surface, then the glass medium would have extended to even a longer range, and then the final image would have been formed by this refracted ray meeting at point I1. But now because there is again another surface LP2N, so the light ray just bends away from this normal at this surface and meets the principal axis at a closer point I, right? So there are two refractions which are happening at surface LP1N. There is one refraction for which we are writing this equation. This is the case. Image is formed in the denser medium, because if there is no second surface, the image would have been formed in the denser medium of the glass. So for that we have one result, but there is another surface, so therefore for that the object is lying in the denser medium, because the light ray initially it is traveling in the denser medium and the image is formed in the rarer medium. So for that object is in denser medium, or we can say virtually the object is in rarer medium. This image I can also be regarded as the virtual image of the object I1, because the initial ray for this surface LP2N, it was coming along this refracted ray. So we can say that the virtually the object is placed at I1, virtually, not actually but virtually, for which the final image is formed at point I. So that's why we are getting a minus sign here as well as here, and we have a different result for that. So therefore we get two equations. Now our task is just to solve these two equations. We just add these two equations in order to get this final equation. On substituting the values according to sign convention, we get this equation. So this is all what just we have discussed. Now the next step towards the lens maker formula, we are just simplifying this. On this side we are dividing the numerator by the denominator mu1. So we are dividing mu1 by mu1, so it is mu2 upon mu1 minus mu1 upon mu1, which is 1. So that's why here on the left hand side we have this minus 1 upon u plus 1 upon v, which is equal to mu2 upon mu1, which is nothing but mu, because one medium outside this lens we are taking it as air medium, so it is mu2 upon mu1, which we can simply write as simply mu. Here mu1 is the air medium, mu2 is the refractive index for the denser glass medium, minus 1, and inside the bracket we have everything same. So we are just writing mu in place of mu2 upon mu1. So we are getting this final result. This is the result from where now we can proceed for the lens maker's formula. For that We are just applying a special case, that what when object is kept at infinity. So for the example, if an object is at infinity, then its final image through the lens will be formed at its principal focus, right? So it is called as the principal focus. You can imagine this situation. For if object is at infinity, then its image would have been formed at the focus, called as the principal focus. So for because object is at infinity, so its distance is infinite, and v, the image distance, because image is formed at the focus, so v, the image distance, will be equal to plus f according to sign conventions. So whenever we substitute these two values here, so 1 upon infinity, it just gives 0, and 1 upon v means 1 upon f. So on the left hand side we have 1 upon f, and on the right hand side everything is same. So this formula, which relate the refractive index of the material with the focal length we are going to make a lens of, right? So this formula, this relationship between focal length and the refractive index, it is called as the lens maker's formula, the manufacturer's formula, lens manufacturer's formula. So the manufacturer or maker of the lens makes use of this formula in order to make a lens of particular focal length by making use of material of given refractive index. Further, when we compare these two equations, we can just see that right hand sides are same, so therefore their left hand side will also be same. On the left hand side we have minus 1 upon u plus 1 upon v, which is equal to 1 upon f. So this, it is called as the lens equation. So this is about lens maker's formula and the lens equation from there. So we have just seen that the steps, there are only few steps in order to derive the lens maker's formula. Only the thing is that we have to remember this formula by some method, right? Once we remember these two formulas, each and every other step is quite easy to follow, because we have to just add and then substitute the values according to sign conventions and make a or we can say impose this special case, and we get a lens maker's formula. Further comparing this lens maker formula with this final result, we can also get the lens equation, which we will derive in the coming step. Here we have some important conclusions or results to remember. What is first principal focus? First principal focus, it is the point on the principal axis of the lens, whether it is convex lens or it is the concave lens. It is that point on the principal axis at which if object is placed at that point, then its image would have been formed at the infinity. So that point on the principal axis where if object is placed, the final image is formed at infinity, that point is called as the first principal focus. And what is second principal focus? Second principal focus is the point on the principal axis of the lens at which image is formed if the object is placed at infinity. So these are the 2 points. However, they are identical. So therefore, we simply call them as the focus. So you must remember that whether it is a convex lens or a concave lens, you will get the same lens maker's formula and the lens equation always. Now we can proceed to derive this lens equation by the geometrical method, just like this. For this, we have a lens here, its optical center, see, it's f1 first focus, f2 the other focus, 2f1 first center of curvature, 2f2 the other center of curvature, right? So object is placed between C and the focus, C and F. So its final image will be formed at the at a point beyond the center of curvature, right? So in order to derive or draw the ray diagram, we just draw two light rays from the topmost point of this object A. So first light ray will be parallel to the principal axis, which after refraction through this lens will pass through the focus, Another light ray, it may be incident at the center of curvature, or it may be incident passed through the focus, but it is convenient to take the light ray which is passing through the center of curvature, because this light ray will go undeviated and it will meet the other light ray, refracted light ray, at point A dash. So A dash will be the image of this point A. So in order to get the image of this object, we just draw a perpendicular from this point A dash on the principal axis, so that it meets at point B dash. So A dash B dash is the final image of this object A B. Similarly, you can draw all kind of images which are found by the convex lens for the objects placed at different distances. You can draw the ray diagram for the object which is placed at infinity, for any point beyond the center of curvature, right, between C and F, as just drawn here, at focus closer than the focus. So you can draw all the light rays images by using these two light rays. So you will get the different kinds of images and their nature. So this point, it is called as M here, and from M we draw a perpendicular which meets the optical center of the lens, right? So now from this notation, now we can draw the lens equation. Lens equation, it is nothing but the relationship between the object distance, image distance, and the focal length of the lens. We can make use of this lens equation in order to calculate any one if we know any two. So let us proceed. First, we take two pairs of the triangles which are similar. For the first pair, we have A, B, C and A dash, B dash, C. So these are the two triangles which are similar because their corresponding angles are equal. So whenever corresponding angles of two triangles are similar, equal, they are said to be similar, and hence the ratio of their corresponding sides will be same, which we are writing as here. So it is A dash, B dash upon AB, which is equal to CB dash, CB dash divided by CB. So this is the first equation we get here. Similarly, let us take another pair of triangles. It is C, or we can say MCF2 and A dash, B dash, F2. So these two triangles are again similar. These two triangles are the again similar because their corresponding angles are also same. So therefore the ratio of their corresponding sides is also equal. So A dash, B dash upon MC, which is equal to B dash F2 divided by C F2, right? So here MC, it is nothing but AB. So therefore in place of MC here we are just writing AB and no other change we are doing here. So this is the only this is the second equation which we get from the second pair of the triangles. So this is one equation from one pair of triangle. This is the second equation from second pair of triangles. Their left hand sides are same, so therefore their right hand sides would be same. So therefore CB dash upon CB, it is equal to B dash F2 upon CF2, right? And because we take all the distances from the optical center of the lens according to sign conventions, so this is the only term which is not being measured from the optical center. So we just convert it to CB dash. So it is B dash F2, B dash F2. So we have to convert it. So how do we write it? We write it as CB dash minus CF2. CB dash minus CF2. So the remaining length is B dash F2, right? And all other terms are same. Now what we do, according to sign convention, we substitute the values and make some calculations or simplification, and we get this result, which is the same result as we have discussed earlier here. So it is the same result, right? So we get 1 upon V minus 1 upon U is equal to 1 upon F. Earlier the term containing U was written first and then the term containing V. There is no difference between the results, right? So this is called as the lens equation. Now comes the final term, which is the linear magnification, which you already know, as in case of reflection from the spherical mirrors, just like that. So linear magnification in meaning it is same. So linear magnification produced by a lens, it is defined as the ratio of the size of the image to the size of the object. Or in general, you can say that the linear magnification, it is the term which compares how large the size of image is in comparison to the size of the object. So it compares the size of the image with the size of the object. So by notation, we write it by small m, which is equal to I, the size of the image, divided by O, the size of the object. So this is the formula for the magnification by definition. We can write another formula for the linear magnification produced by a lens according to this. For a lens, we were getting this relationship earlier, right? Here, we are going to make use of this relationship. Here a dash b dash, it is nothing but the size of the image, and a b, it is nothing but the size of the object. So we are going to make use of this formula, which is cb dash upon cb. Right? So according to sign conventions, on the left hand side we have I upon O, and on the right hand side we have V upon U. So therefore we get another formula for the magnification as V upon U. So we can make use of either this formula if situation permits, or the other formula, magnification it is equal to V upon U, if the values are given accordingly, right? We can also transform this or put this magnification in terms of two more forms by making use of this lens equation on the right hand side. So from the lens equation, here we substitute the value of u, and we get the magnification in terms of focus, focal length, and the image distance. And if we substitute for v the image distance in this formula, then we get the magnification in terms of u and f. It is u here, right? Means object distance and focus. So we get two another formulas from this same situation. So for the magnification, we have 1, 2, 3, and 4. These two formulas are easy. From the, we can write the value of v or u from the lens equation. So from the lens equation, in first case we have found the value of u, and we got the value of u in terms of v and f. So therefore magnification we have got in terms of v and f, the image distance and focal length. Similarly, if we substitute for v in this from this lens is same lens equation, then we get the magnification in terms of u and f, the object distance and the focal length. So therefore we get different formulas for the linear magnification. And final term here, it is the power of a lens. Because lens has the ability to converge the light rays or diverge the light rays. So in order to measure its ability, that how close or how farther a lens can converge or diverge the light rays, right? So in order to measure that ability, we have a term called as the power of the lens. So power of a lens is ability to bend a ray of light, right? Power of a lens is its ability to bend a ray of light falling on it, and it is found by the reciprocal of the focal length. Because shorter is the focal length of the lens, it means that lens is able to converge the light rays at a point called as the focus, which is closer, right? So it has more ability. So more is the focal length, shorter is the power, or we can say smaller is the power, and shorter is the focal length, more is the power of the lens. So by definition, we can also write the power of a lens as the reciprocal of the focal length. So if focal length, so this is the formula for calculating the power. Now you get different formulas and you can compare all these in order to get different results. So what is the units for representing the power of a lens? If focal length, it is in meters, which is in SI system, then power will be in terms of per meter, which is also called as diopters, which we write as diopter as a complete or as a single letter capital D. So this is about power of the lens. That's all about this class. Thank you.